consistently holding above 40, so we should be meeting that or exceeding it.
No wonder. Okay, right, first let me make an apology. Hello, can everyone see me okay? Right. I'm just looking to see the YouTube catch up. We're streaming now to the right one, are we?
Seems to be.
Yes? Okay, wonderful. Apologies, folks. My dumb ass made the mistake of clicking on day 2 manipulation instead of day 1 session 2. So we are now here, and I'm going to hand over to Chris, who's going to give his introduction again, over to then Mark, who is going to give our keynote speech, and we'll start again. My apologies.
Thank you, Ollie. Yeah, so I'm Chris. I am going to be leading the second session. The theme of this session is mobile robotics. We've got a great selection of projects that really show the breadth of mobile robots, from delivery bots to swarms to smaller like educational robots. We are very pleased to have Mark Emerton of UK Research and Innovation here with us today, presenting on UK robotics for safer inspections, maintenance, and repairs. Mark is the Senior Innovation Lead for Robotics and Artificial Intelligence at UKRI, and he primarily supports the Robots for a Safer World program. Mark.
Thank you. Hello everyone and welcome. My name is Mark Emerton. I'm here to talk about some exciting British mobile robotics projects that have been funded by UKRI. I'm going to talk about funded projects that have put robots 4,000 meters under the ocean, into low Earth orbit, and flying in the skies over Chernobyl. I work for Innovate UK, and we're the UK's innovation agency. I'm one of the 500 staff that help get grants, loans, and other innovation support into the hands of thousands of companies across the country. My background is a systems engineer. I've specialised in unmanned and autonomous systems, previously in the defence industry, but now I'm passionately working to accelerate the adoption of robotics across all sectors of the economy. I'm a field worker, which means I visit companies we fund across the country to learn more about their projects and make sure that British taxpayers' money is having the biggest impact possible. Innovate UK is part of UKRI, UK Research and Innovation. We're the industrial arm of that organisation. We primarily give grants to businesses or business-led consortiums that might include universities and research and technology organisations. The other research councils are funding the academic researchers at lower TRLs. They seed the workforce with skills and increase the state of the art. In robotics, we at Innovate mostly work alongside the Engineering and Physical Sciences Research Council, and I'll talk a little bit more about some of the academic research hubs that they funded. My day job at Innovate UK for the last 4 years has been to help run the Industrial Strategy Challenge Fund Robots for a Safer World Challenge. It's about robots in extreme and hazardous environments, places where it's dangerous, impossible, or unproductive for humans to go, especially in the nuclear, offshore, and space sectors. Challenge funds are different to how we normally fund research and development. We define themes and set up more structured environment for multiple companies and universities to collaborate. Rather than keeping businesses largely in isolation, we've built a cohort of over 200 organisations across the UK now, networked together. Robots for a Safer World is a £112 million challenge that was launched in 2017, and we're in our final year. We've funded over 100 Innovate UK projects, spanning the whole breadth of the UK. For those who are outside the UK, this map here is not what a map of innovation projects across the UK normally looks like. In the past, a big proportion of the R&D has been clustered in a small region of southern England between Oxford, London and Cambridge, and we're changing that. What's more, these dots are not just the registered offices of the companies that we funded, and the work being carried out is taking place over an even more diverse range of locations. Through EPSRC, we've funded 4 academic research hubs: the Robotics and AI for Nuclear, Offshore Robotics for Certification of Assets, National Centre for Nuclear Robotics, and Future AI and Robotics for Space. Hundreds of students across the country will have worked on projects funded by those hubs. Finally, we've had some remarkable company successes, with examples of businesses who have gone from just 1 or 2 co-founders who've now gone on to raise millions of pounds or won huge contracts, and they're starting to scale. In the first 3 years of the programme, we really focused on those 3 market opportunities in offshore, space and nuclear, but also funded some projects that had cross-cutting benefits across a wide range of sectors, things like using drones or pressure vessel inspection. But COVID came along last year, and it shook things up just at the time that we were extending the programme for a further year. COVID showed us that robotics wasn't just important for those extreme environments. Innovate UK ran a grant scheme that received thousands of applications in the space of just weeks in the midst of the pandemic. Many of these were from companies wanting to use robotics to keep their businesses alive with a hugely disrupted supply chain and hugely disrupted workforce. Robotics, then, was shown to be a crucial technology for national resilience, not just productivity and safety in extreme environments. With that, we changed our scope, and we've invested in robotics projects across other areas like healthcare, logistics, agriculture, and construction, as well as funding projects that tackled the impact of the pandemic itself. But let's go back to the areas we focused on at the start of the challenge and continue to fund. In the UK alone, there are over 2,000 offshore wind turbines, and the wind sector produced a quarter of all of the electricity in the country in 2020. But these turbines need inspecting, particularly the blades, the tips of which can spin at hundreds of meters per second and get eroded by rain and damaged by lightning strikes, or just have manufacturing defects that need to be monitored over their lifetime. But at the moment, you need to send a rope access technician out to sea, because the environment is so dangerous that's slow and expensive work. You could use a drone to visually inspect turbine blades, and we've funded a few companies looking to make better use of drones for turbine inspection. Or there's companies like Bladebug Limited, who are a London-based startup who've developed this crawling robot capable of contact-based assessment and even minor repairs. On the surface of the water, we funded companies like HydroServe, who have built a very small, low-cost survey vessel for inland waterway survey tasks, and also larger platforms for offshore surveys too. Where previous unmanned survey vessels have been based on larger crewed craft, what they've built here is small, low-cost unmanned platforms designed to be unmanned from the beginning. The platform's small size means it's inherently safer to operate and more portable between sites and quick to set up. It can be adapted for a wide range of tasks, but typically it's well suited to hydrographic surveys, giving customers highly detailed hydrographic scans. Below the water, Bristol-based Rovco have shown tremendous growth from a startup to now an industry leader in the subsea inspection services market. Their SubSLAM technology has moved the state of the art from basic ROV video live feeds to 3D reconstructions of underwater scenes, and now live 3D reconstruction, which allows operators to carry out measuration tasks and even machine learning based object classification of what they're looking at. Above water, some of the stuff is now relatively trivial with modern LiDARs, but underwater it's a much more challenging task. The ability for ROV operators and engineers to have access to live 3D reconstruction of their assets is proving extremely valuable. As well as funding high-growth startups, we've also awarded funding to a collaboration between Soil Machine Dynamics and Newcastle University called TeamTau to enter the Shell Ocean Discovery X Prize. If you don't know about the Ocean Discovery X Prize, I'd encourage you to go and check it out. But it was basically about mapping the deep open ocean floor to 100 times the resolution of previous methods. Most of the teams entering with the challenge used large, expensive, conventional autonomous underwater vehicles. But TeamTau used a combination of a small, uncrewed catamaran vessel that could dispense a swarm of small, vertically swimming AUVs, which each propels itself to a depth of up to 4,000 meters, scanning horizontally as it descends before returning to the surface to be then recovered by the mothership. It's all about using a CubeSat-like philosophy of dramatically reducing the size, cost, and complexity of the system. The team won a Moonshot Prize at the X Prize Awards for innovation at the X Prize, and it's shown the UK's innovative engineering on the world stage. Moving on from the offshore environment, we're now going to go into orbit, and the graphics here are a visual representation of the concepts of operation for Astroscale's LCD demonstration mission. This will be a world-first demonstration of a commercial mission to capture a satellite and safely deorbit it. Space debris is one of society's great looming problems. Low Earth orbits are becoming dangerously busy, and a big collision risks starting the frightening Kessler syndrome, where a chain reaction of satellite collisions that could render an entire orbital plane unusable. Astroscale is an Anglo-Japanese startup. They launched their satellite to orbit in March of this year, and you can follow them on their journey to demonstrating how to decommission customer satellites and safely deorbit them, even if the target satellite is completely dead and tumbling in space. The mission is being controlled from the Satellite Applications Catapult here in Haurt, UK, and we've funded the development of that control centre. In addition to this exciting project, we've also funded several other space innovation projects from the companies listed here. These include things like demonstration for how satellites can be assembled by robots in space. The third and final key area of the first few years of the challenge is in nuclear, particularly nuclear decommissioning. The National Centre for Nuclear Robotics, one of the academic hubs I mentioned earlier, made the news a few years ago with a trip to Chernobyl, where they used a mix of fixed-wing and rotary-wing drones fitted with radiation sensors to fly over regions of the Red Forest near Chernobyl and produced a vast improvement in the resolution of radiation maps of the region. And we've worked alongside the UK's Nuclear Decommissioning Agency and Sellafield Limited, who are responsible for decommissioning the UK's legacy nuclear waste, to fund a diverse range of projects, all tackling different parts of the 132 billion 120-year task. And these companies and organisations are widely respected for their capabilities, so much so that many are working in Fukushima in Japan too. One of the SMEs at the forefront of this industry is Createch Limited, who among other things are working with the Boston Dynamics Spot platform in nuclear environments. We have a specific project focused on an Anglo-Japanese collaboration on nuclear decommissioning of Sellafield, the Jet Fusion project in Culham, and Fukushima, called LongOps. This project is based at the RACE lab in Culham and will invest in research at universities and technologies developed by SMEs, and will develop new approaches to robotic decommissioning, particularly around the use of digital twins and training manipulator operators. LongOps is running for 4 more years, and procurement opportunities for R&D will be opening from August 2021 onwards. If you're working in robotics, even if it's not in the nuclear sector, I'd encourage you to go and check it out. I'll get some links sent out by the organisers. Finally, a shout out to the RAIN Hub, as well as lots of exciting research, including testing an ROV at the Haurt test facility in Fukushima. Throughout the pandemic, they've run these technical webinars every few weeks, keeping the community connected and informed about all the great research. But hold on to your papers, because if you're a fellow scholar working in this field, you can go and check out these webinars on the RAIN Hub website. There's everything you could want to know about the entire state-of-the-art nuclear robotics, from pipe crawling robots to simulation environments, legged robots, HMIs, mapping, guest webinars from industry leaders like Rolls-Royce, or the other robotics hubs that I've mentioned in this presentation. You name it, it's a fantastic resource and a great way to get inspired by the research or find other academics to network. So, now for something completely different. Along came COVID, and it changed stuff. Robotics was there to respond in several interesting ways. Drone delivery concepts have been around for a decade or more. The only place where previously they'd really scaled properly was Zipline in Africa, delivering medicines and vaccines. But COVID meant there were some more specific challenges that suddenly made drone delivery concepts make absolute sense. We funded projects that delivered medicines and test kits to hard-to-reach parts of the UK, like the Isles of Scilly or the Isle of Wight. We also funded several robotic cleaning concepts, whether that was disinfectant spraying, hospitals or airports, UVC disinfection concepts, and even just using swarms of robot hoovers in care homes. But COVID made us realise something. Along came this sudden shock and disruption, and a whole range of new opportunities for robotics to be used to mitigate these effects. But a significant proportion of the UK's robotics R&D spending had been in areas that remained really important, but couldn't easily be pivoted to respond to new needs quickly. So we wanted to change that, not just for COVID, but also for ongoing fight against climate change and towards the UK's pledge to reach net zero carbon by 2050. We needed to support some of the pivoting from these extreme environment industries towards new challenges. To help that, for the last year of this competition, we launched the Robots for a Resilient Future competition, which has funded 38 new projects in a wide range of industries. These include things like agriculture. We've got 10 examples of British robotics companies developing systems to harvest or monitor different crops or pick fruit. That's stuff that's always been previously really hard to automate, as it's always been picked by hand. The UK has typically brought in thousands of seasonal migrant labourers to pick our crops. And in summer 2020, the agricultural sector was worried, not just for that season, but for the future as well. Robotics is an answer in the long term, but that means developing a whole range of new approaches. All these vegetables and fruits are picked in subtly different ways. During the pandemic, and as part of Robots for a More Resilient Future, we've also funded a few examples of general-purpose remote working robots, typically VR and haptic glove-controlled robot arms, allowing workers who work physically to do their job remotely. Some people might recognise that guy, but the highly dexterous hands are developed by the Shadow Robot in the UK. We funded them in projects such as replacing human hands inside radiation glove boxes, but this technology is inherently general purpose, and they work across a whole range of industries. The construction sector in the UK, although plagued by logistical problems, carried out throughout the pandemic. We funded a few companies like Birmingham-based startup HouseBots, who have developed this wall-climbing painting robot capable of painting or applying spray exterior treatment coatings to homes or other buildings quickly, without any scaffolding, without any humans working at height. I want one. If you want to find out more about the whole programme, including hundreds of projects I've not had time to mention, please check out our programme brochure. It's a delightfully old-school PDF of what we thought would be sending and taking to exhibitions throughout 2020 and 2021, handing them out in person on paper copies. Yeah, that didn't quite work, but you'll see in there, you'll see some descriptions, imagery, and some contact details of every grant that we've placed, and we try to keep it updated. You can get that on our website, and I'll make sure that we send some links out. And we don't just fund companies to do R&D, we support in other ways too. One of these is in supporting infrastructure. In June, we announced the first phase of funding towards the development of the UK Robotics Proving Ground. We want this to become the Nürburgring of robotics, a world-recognised facility where companies and researchers can come and test and showcase their equipment, where new performance records can be set and customers can learn more about the state of the art and increase their confidence and understanding about how robots can change their businesses. We're spending the next year launching a consultation with UK robotics industry, both the suppliers and the customers and the public sector, to understand what their specific needs for such a facility might be. I'll send out some links to learn more about this as it evolves, but we want to hear from everyone about what this facility could do for you. I hope I've inspired you over the last few minutes, or at least given you some interesting links to follow up on, or some projects to learn more about. We're in our final year of our £112 million programme, and we've achieved a huge amount. But it's fair to say that robotics is still only evolving quite slowly right now. And in many of the examples of where robotics could have been able to step up to society's challenges that COVID gave us, we as a technology sector just couldn't act fast enough or be cost effective. We're a messy collection of lots of different technologies, and with every application of robotics, a whole new approach and often new research is required to tackle the challenge. Robotics, therefore, is not just about extreme environments, even though the value propositions there are really clear, but it's going to increasingly be about national and international resilience as well. We need to accelerate robotic development. We need to reduce the cost of robotic products and services. We need to reach entirely new market verticals. So how can we do that? Well, in the UK, we can do more industry-driven innovation. That's more Innovate UK grants, but also encourage more private equity investment. The UK simply doesn't enjoy the same level of VC funding available as is in the US, and we need to do our bit to change that. We urgently need more skills and more diversity in robotics. British robotics firms struggle to attract and retain talent. It's not just PhDs either, it's graduates or apprentices. It's experienced people from other sectors. We should work hard to get more women and non-binary students into robotics to make sure we can sustain the growth of the sector that it's ready for. We need to carry on doing more fundamental research and make sure this gets pulled through into startups and spin-outs. We should invest in physical infrastructure like test facilities and proving grounds, as well as living labs where very high TRL systems can be experimented with alongside the public. We should invest in digital infrastructure like digital twins, simulations, software standards, and open source projects that promote modularity and reuse of code. The public sector can and should lead the way as first customers for some novel robotic system concepts, helping SMEs get crucial early revenue before they can secure more investment and scale into commercial applications. Finally, there's an opportunity to create centres of excellence to bring together robotics researchers and industry to work on how robotics can tackle new societal challenges like climate change and net zero, healthcare in an ageing society, autonomous logistics or in-orbit servicing and manufacturing. That's the end of my presentation. I want to thank the organisers of the Reddit Robotics Showcase. I don't spend much time on Reddit because, like a lot of social media, it's designed to be an almighty rabbit hole. One moment I'm learning about some cool robotics projects on r/robotics, and the next I'm reading about the latest meme stock, and I don't even know how I got there. But you can connect with me on LinkedIn, where if you are in the UK, you'll be keen to hear about some of the next funding opportunities for British robotics researchers and innovators. And if you're not in the UK, you can keep up to date about some of the investments that we've made and find out how you can connect with those companies. I'll send out a range of links for some of the stuff I've talked about today, and I very much look forward to hearing your Q&As and the rest of the sessions today. Thank you everybody for listening, and thank you again to the organisers, and I look forward to having your questions. Thank you.
Thank you so much, Mark, for your presentation. I have to agree, Reddit is definitely a time sink. Probably be a lot further in my studies if I didn't spend so much time on there. We've got some questions from YouTube, but first of all, I wanted to ask about that last slide you had. You had things we need and how to get those things. I want to ask, how do we get that second step? What things are needed to accomplish those steps? Is it funding? Is it support from the public? What practical resources are needed for that?
So it's fair to say that funding is always going to come first, right? So that provides it provides us as public servants to help run these programs. That's certainly the case in the UK. And also then it allows us to fund charities, research organizations. It means that we can essentially do all of the stuff that we've been talking about. So everything that I've just presented there, although all of the fantastic work has been done by innovators, it's all been supported in the UK by taxpayers' money. And we have to justify what return on investment that's getting for the economy. And actually it can be quite a brutal economic hard fact that we have to do. We have to say we've just spent £112 million over 4 years, and we have to convince Her Majesty's Treasury that we want to spend more because it's actually having a net return for the economy. I appreciate that in different governments around the world, innovation funding works in a really different way. So I can only really speak to how we do that in the UK, but what we need to do is secure funding for a new program, but also make sure that we've just got a really good, diverse range of interventions, so that different companies of different size can do the R&D that they need to do at different TRL stages. And also we start to do some new things like more research on the societal stuff. So that we can actually understand what impact robotics might have on different parts of society and different parts of the economy. So that's a really complex question, but it's essentially one that we're in the midst of answering at the moment. So because we've largely committed all the funding for our program, we're out monitoring the companies that we've funded, but the other half of our day job is about securing a whole new program, which at least in the UK means it's actually about going to government and getting funding from there. So that's right. That's right. Exactly what we're doing right now is putting a case together to government for why we should continue to invest there. The other thing I should mention is that in the UK, the government has just published the innovation strategy. It's a big document that essentially outlines what the government's policies are on innovation. And the one brilliant thing for robotics, they're calling it robotics and smart machines, is that that's one of 7 very key technologies that are at the highest priority for the British government. What we now need to do is work a level below that and actually explain to government what kind of research interventions we need in order to continue to be up there with the rest of the countries in the world in terms of how well we're doing and how we can grow that. So really, the short answer to that question is that's part of the day job, is working out how that works.
All right, thank you. That was a great answer. A question from YouTube. How much does UKRI promote communication between these different sponsored projects? Is there a need for them, or would there be a benefit for them integrating their work together for innovation?
Yeah, so that's a really interesting question. So sometimes we'll do that after the fact. After they've done a project, we will run showcasing events, networking events to get them talking about what they achieved and what their next steps would be. One of the things that we've done throughout the whole life of the program is we've run an annual cohort event. This year is obviously virtual. In the past, that's always been in person somewhere. And actually at the virtual event, we had over 500 attendees there showcasing the work that they've been doing. So there's some after the fact work in terms of collaborating about their achievements and their next steps, but we also encourage collaboration and sharing before those innovation projects even happen. So whenever we launch a new competition for funding, we will typically have a briefing event, which will include some kind of networking activity to see if we can form new collaborations between companies, maybe a company and a university to work together. And then also something that we've done in 2 cases over the last 4 years, we've run something called an innovation lab. That's not going to be something familiar to most of the people on the call today, but essentially what we do is we get people to apply to a residential workshop. And we get 30 people and we lock them in a hotel room for a week. And some of these people have never met each other in their lives. And at the end of that week, they produce new research proposals and they could be funded. And we've actually had several instances of companies and businesses that have never spoken to each other before in their lives. And within a few weeks, they're working on a project that's funded to multi-million pounds. And they're working together for the next 2 years. And we've had some tremendous success with that, including one startup that was really just 2 people strong, came to one of those workshops, and it was the start of their journey, and they started scaling from there. So sometimes we take quite a hands-on approach, but yeah, collaboration and communication is absolutely key, and it's a big achievement for us is that before we really started, the robotics community in the UK was quite fragmented. People weren't really speaking to each other. But now through these annual events that we've been running, the community is getting warmer and warmer and closer, which is great. So I think we're moving the dial on that, but we've got to keep doing more of that in the future as well.
Can I pop in with a quick question? I know it's a bit outside of your scope of the Robots for a Safer World Challenge. At the end, you mentioned EDI. Does the UKRI have any funding or any groups set up? What do they have set up in place for promoting that in academia and industry?
So it's no huge surprise that that's massive at the moment, right? I don't think I would do justice to all of the different ED&I efforts that are going on, particularly in Women in Innovation. Innovate UK has a really successful Women in Innovation program where the focus is on women-founded companies and to try and make a difference there. Because actually, the statistics in terms of the number of women-founded companies and how many get funding is actually really shocking. So the Women in Innovation program is hoping to change the dial there, and local to home in terms of robotics and in most engineering subjects, the ratios in terms of gender entering university are really bad. And so we're quite keen to try and see whether there's some focused intervention that we could do there. If not necessarily doing positive discrimination towards women, perhaps mandating a 50-50 split in some of the stuff that we do. So we still need to work out exactly what policies to take. And I think some of those are still, the best practice is still not necessarily understood. But the key thing now is that all programs across UKRI, every single program across UKRI needs to consider ED&I. So every time we go to try and fund something new and we put in a case for that, or a business case that goes into government, we have to address how ED&I is working. And that's in terms of gender, it's in terms of race, and in the UK, it's also in terms of regional inequalities as well. So it is soon becoming one of the highest priority things in terms of what we do. But I'm probably not the right person from UKRI to speak about all of the different ED&I policies that we have.
Okay, thank you very much. It's going to be our main priority for the Reddit over the coming year. It's something that we have learned about in light of this event. When we then were finally putting together the website, we took a look and realised, oh, okay, right. So that's our big thing for next year. I'll get in contact with you about that at some point in the future. Thank you. Back to you, Chris.
Yeah, thank you for your question, Ollie. We have another question from YouTube. So they say a lot of the difficulty with these kind of competitions is moving them from the competition to like industry and practical applications. Do you have any ideas on how to streamline that kind of process?
Well, I don't know whether the question came from the UK or from elsewhere. I think one of the things is that when government run competitions in the US, and my limited experience of this is, say, a DARPA running a competition. It is exactly that. It's a competition. There might be prizes, there might be some kudos when you do that. But as you say, transitioning out into a real industrial application might be quite challenging. What we do in the UK is not usually that. We don't tend to run competitions as if they're prizes or challenges per se. Every application for a grant from Innovate UK has to have quite a robust business case in there. And we track the exploitation of those projects all the way through, and we make sure that those companies are updating what their business models are and speak about who they're targeting. So actually, we try to make sure that as a company transitions off of one of our grants, that they actually have their commercialization route like right there. We try to minimize that valley of death as much as possible. That said, it always still seems to be there. The valley of death doesn't always just disappear, but it is something that we make sure is baked right into our process. Even down to the assessors of our grant proposals, they have to spend time thinking about what the business case is, what the exploitation route looks like. We need to fund stuff that is technically risky, because the government shouldn't be subsidizing easy R&D that any company can do without needing any funding. So we need to identify what's technically risky, but we want to make sure that the commercialization route is clear, and that there's a really good value proposition. One of the things that I say to companies that I'm visiting, if they are struggling to explain to me why they're doing it and how they're going to commercialize it, I ask them to speak to me as if I was an investor or a VC. So although we're providing funding, we don't take any equity stake. So we're not really VCs, but I want to be like that in the sense of I want to have a warm feeling that their commercialization route is there and their business plan is solid. And if we don't have that, then that's not the type of project that we all try and want to fund. And so that's how that might differ maybe to how government-funded competitions might run in the US. For us, it's actually more a grant to a business to then go and take their R&D forward to commercialization, rather than maybe like a DARPA grant challenge, for example.
That's an interesting difference. I didn't know that distinction between competitions. Yeah. Do we have other? That's all the YouTube questions. So, oh wait, we just got one more. Do you find that teams have more difficulty with software or hardware in these challenges? Hardware. Yeah.
I mean, that's pretty clear. So it is often the way where now, obviously, software in robotics is challenging, and that can cause a whole bunch of headaches. But I would say where they encounter problems that they didn't necessarily expect when they were writing their application or what they had in mind, in my experience, it's almost always hardware. Software problems are rarely completely unsolvable, right? I'm not aware of very many projects that have completely failed because they can't get the software right. Whereas I know lots of examples of where they just can't get the hardware right. And also it tends to have a bit more of a yes/no impact on whether something is financially feasible or not. Maybe we fund them to run a feasibility project and they get to the end of the project and they go, in order for this to work, we need to be able to make this robot for less than £10,000. But we found that the hardware just meant that we couldn't get it for less than 50. And as a result, it's not really commercially feasible. Whereas software development costs can obviously go up. And actually, it's probably something that businesses have to tackle after they finish with our funding, because maybe they run prototype code that's maybe a bit buggy, but it doesn't matter. They get the point across. They're going to have to spend some of their own money to get that code running right. But I'm personally not aware of any projects that have completely fallen over because of software. Often it's a case of just maybe hiring some more experienced software engineers in order to take their prototype to commercialization. And that's expensive, but it's all doable. Whereas I'd say the hardware has always been the more challenging aspect.
Do you know if there's a commonality, a common theme in the hardware at all? Is it one specific area where there always seems to be a letdown?
I'd say the only common theme that I'm encountering is just that there are very few simple modular components that people are dropping in. I mean, I use that example of the 10 agri-tech robotics projects that that we funded in the recent year. All 10 of those platforms are using, all 10 of those harvesting robots that go out into fields and pick different vegetables. They're all using a different rover. There is no standard rover platform that you can just go and buy. They're all having to spec their own motors, their own motor encoders. They're writing some of their own code to control those vehicles. And it's kind of that was probably one of the big commonalities. I've not really seen a project that's been able to just take a bunch of ROS modules, throw them together with some off-the-shelf components, and away they go. It's just the commonality I've seen in terms of hardware challenges is just buying stuff and bolting it together. And that's kind of one of the things I put there in the end in terms of something we urgently need to try and fix as a whole community, not just the UK, is how to get this stuff to glue together and function a bit more like Lego. More commonality, more modularity, so that these projects are not having to reinvent the wheel every time they want to make a robot. And I think that's kind of everyone's experience at the moment. If I told any of you guys on the call, I want you to make me a robot by tomorrow and I want it to do this, you're not just going to be able to grab a bunch of parts out the parts bin and throw it together. Everything's still being really hand cranked. And actually that's slowing companies down so much. And that's my point in terms of the COVID thing as well. We had hundreds of companies being invited by hospitals, for example, to say, hey, can you just build me a robot to move some drugs from our pharmacy to our COVID ward? They just couldn't react fast enough because everything's, they're having to hack together motors out of e-scooters and stuff. It's just the supply chain isn't mature yet. And I think we need to really try and move the dial on that.
Yeah, in the same way that you have ROS with the plug and play ability for putting together software, we need something a bit, as a kid, I got into robotics through the Lego Mindstorms competitions, and we, the big kids version of that, because then it'll be just as fun as it was back then as a kid too.
I know, and you know what? I think everyone comes back to Lego because it's like, Lego Technic, Lego Mindstorms, they were there in our childhoods, and now we're here as engineers. Funnily enough, it never works like that. We're soldering PCBs and wondering like what went wrong. So yeah, that's for me. And actually, there are lots of others in the robotics community who are crying out for the same thing. Now, ROS is getting there with software. There are still lots of industries that are not quite ready and not quite touching ROS, and that's fine. But you should never underestimate the difficulty of trying to introduce new standards. And I'll remind people of a really good XKCD comic. I don't know if we can just like flash it up somehow, but it's that, oh my God, there are 23 standards for this thing. We should make one new standard. And then the next slide is there's 24 standards. And so, yeah, trying to standardize and build modularity into robot hardware is going to be inherently difficult. But, for me, whether it takes 5, 10, 30 years, if we can eventually get to like a Lego Mindstorm plug and play, build a robot in a day type situation rather than months of prototyping, that'd be fantastic. But I think we need to hear more from the industry about how we do that, because that's, I think, one of the biggest prizes, and something we really do need to do is try and make this stuff more like being able to produce a website where you can just bolt together a few different tools and away you go, publish. And robots is so far from that at the moment, but I think we can get there.
Yeah, so does that drive for standards need to come from the industry or from perhaps like an outside organization like UKRI or another like government side?
Government imposed standards, it's a dangerous way of doing it, right? We are well known to be sometimes quite slow to react to new technologies, and that's not usually the best way, right? So I'd say probably something that's more open source is more likely to be better. You don't want a system where private companies can start to have a heavy influence in what that standard is, and they start to skew the market. So that's my own view on that. I don't think government imposed standards is the way forward, not least because the smartest people are not working in government right now. When we go out to visit projects that we're looking at, I've visited hundreds of robotics companies in the last few years. If I'm the smartest person in the room in those meetings, something's wrong. We shouldn't have been funding them, right? So the smartest people are in the robotics industry and in academia. They're not in government, and I don't think that we should be the ones setting the standards. So that's my view on it. But how do you starting a whole new open source project and making sure it can gain traction is challenging. It's something that we've got a community in the UK called the Robotics Growth Partnership, where they bring in some senior industry leaders and senior academics, and they're working on that problem in terms of how to do that. And they're asking for funding to do that as well, because they recognize that while it shouldn't be government-led, those standards, it does require some funding to make sure that that those standards can be developed properly.
Great. Another question, what kind of big ideas should someone keep in mind while working on one of these projects? And should they be thinking towards commercialization, or should they be thinking about the details of the project and that initial presentation?
In terms of when they're applying for it or when they're working on one?
I'd say in the context of your challenge, sure.
Yeah, sure. So we need companies, if they're applying as an industry-led project, to be thinking about commercialization from the outset. We are not the organization in the UK, in Innovate UK, that funds just speculative fundamental research, but the research councils do, and they'll fund PhD students to go and do research projects in certain areas just to move the TRL in the right direction, and just improve the state of the art. So there's really two different things going on. There's academic research, which is also funded by UKRI, and then the industry-led stuff is funded by Innovate UK, and we want to see company growth, and that's how we justify our existence. We spend taxpayers' money because we can show that our funding generates growth within that company, and we get a net return to the economy when we do it. So commercialization is absolutely key, and that's really where you should start. We do still fund feasibility study projects where actually you might be slightly uncertain, and instead of taking a £1 or £2 million grant from us, it might just be 50k, and it's enough to just throw a prototype together and get it in front of some potential customers and just test the water with it. And that's something that I'd say is a little bit easier, requires maybe a bit less detail with the commercialization. But no, that's really important for everything that we fund, is to have what the value proposition is and what route to market there are, but also be flexible with that in the future as well, because sometimes you might find that there's a need to pivot. And this is very similar to how you would go and get seed funding or VC funding anywhere in the world. You would need to convince that investor what the basic business case was.
All right, thank you very much, Mark. That is about all the time we have for questions. All right, the next presentation we have is, let's see, Beshr Eldebuch, who is not present due to time zone reasons. So I'll be showing their pre-recorded video. They're presenting on their fully autonomous indoor mobile robot using VisualSLAM.
Where am I? What surrounds me? These are the questions that every robot asks itself. The answer for these simple questions is found in something called SLAM, or simultaneous localization and mapping. In other words, we need to build a map and to estimate the position and the orientation of the robot. Usually, SLAM is done with the LiDAR sensor. However, VisualSLAM is replacing LiDARs with cameras. The motivation behind this project started 1 year ago when we wanted to participate in World Robotic Olympiad. The mission required a localization system to solve the problem, but we couldn't afford a LiDAR back then, so we started looking for another solution, and here's where we found VisualSLAM. Unfortunately, the competition was cancelled due to COVID-19, but the idea is still in our mind. Rahav Zayat and I have worked on this robot for nearly 9 months as our graduation project at Damascus University, under Professor Raouf Hamdan's supervision. We use the robotic operating system where we can write programs in C++ and Python. This helps us to accelerate our work since it provides a set of tools and libraries that keep our focus on the algorithm itself instead of worrying too much about the code. The project starts with the Kinect camera that streams point cloud, depth, and RGB image to RTAB map, which is the VisualSLAM algorithm that we use, and then RTAB map estimates the position of the robot and builds an occupancy grid map. So since we know our position and our surrounding, we can now move autonomously So we first generate global plan using Dijkstra algorithm, which work on global scale but doesn't respect kinematics and dynamic constraints such as local planner does. So local planner takes into account things such as maximum velocity, minimum velocity, and acceleration, the size of the robot to generate a local trajectory, and sends the desired velocity to motors controllers that keep motors at constant speed using PID controllers. We have three main parts. First, we have the laptop, which runs all the necessary software and then sends the desired velocity to the Arduino, which its job is to communicate with motors controllers using I2C protocol. Then the motors controllers keep motors at constant speed. This occupancy grid map is generated by our VisualSLAM algorithm. We can see that there are three colors: dark gray, which is the area that's not discovered yet, black, which means there's an obstacle in that place, and white, which means the robot is free to move around. Finally, the red arrow shows the position and the orientation of the robot. As for the navigation part, we use Dijkstra algorithm as our global planner, which we can see it as the green path. Usually this plans a path from start to goal on a larger scale, such as cities or countries. You can imagine it as a direction service in Google Map. As for local planner, timed elastic band is used, which generates trajectory that respect the size of the robot, the distance for an obstacle, the minimum and maximum velocity, acceleration, etc. It does so by solving a multi-objective function. Feel free to connect with us on LinkedIn, and thank you all for listening.
All right. That was Beshr's project. If you want to ask questions, you can still put them in the chat, and we'll take all those questions and put them on our final Reddit post for Beshr to answer. A little bit early, but Jason, are you ready?
Yes, I'm ready.
Great. We will have Jason Luke presenting indoor self-driving robots.
Good afternoon, everyone. I hope you can enjoy a wonderful afternoon. My name is Jason. Today, I will introduce my indoor self-driving robot. The indoor self-driving robot is built for performing domestic services. User can command the robot on their mobile devices, and the robot can deliver items around the building automatically. Let's start the live demonstration. I use a couple of ducktails as my cargo, and I'm going to bring them to the area in front of the camera. First, I turn on my I open the web page on my phone. This web page is hosted on the robot through the local area network. Then I choose the destination. Give me 1 second. Yes, I choose the destination and process the. Give me 1 second. There's issues. I'm apologize.
Whilst you welcome that, just keep going on it, and when you're ready to demonstrate, go ahead. I just want to commend you for being able to give a live demonstration. The only other people that have done that so far are a very well-funded venture capital software company, and I appreciate that as soon as you put a camera on the robot, things that shouldn't should be working start going wrong. So if something has stopped working that has been working consistently, here we go.
My bad. Yeah, but the command, there's troubles. Okay, give me a second. I'm afraid I got to wish. I'm afraid I got to I got to
That's okay. If you're not able to give a demonstration, that's okay. But tell us more about it.
Okay. This. Let me share a screen. This is an indoor self-driving robot, and it's performing yes. Hello. Yeah, this is an indoor self-driving robot, and it can bring the items around the building, and it can drive automatically by the cell phone command. It can detect the obstacles, and it can avoid the obstacle by its step camera in front of the robot. Also, I will demonstrate some of the functions are embedded on the robot. Here is
By using visual recognition, the robot is able to get as close as it can.
This robot can fold the trash automatically to the trash can. It's using a color detection to detect the trash can. It has the logo on the trash can, and it can locate the objects. Also, it can return to the. Yes, here is the screen for the mobile command. This is the charging basis. So when the robot returns to their basis, it can charge itself. So we don't need to worry about the battery life. Also, I embedded a scissor lift. Let me just show the pictures. I embedded a scissor lift and a robotic arm to my robot, so it can perform more functionalities. I'm sorry I cannot present cannot show the live demonstration, but this is the end of my presentation, and feel free to ask me any questions.
That is just fine. This was a very ambitious project. You had like an app that you were controlling it with. Can you talk a little bit about that?
Yes, it is the web is hosting on the robot, so everyone inside the same local area network can access the robot. So I'm not using an app. I'm using a website, because if you're using an app, people have to download it. So it will be more complicated. So I decided to use a map so people can scan the QR code or enter the web page link, so they can access the robot immediately inside the room. And also, since this is the local area network, So people from outside the room, they can outside the Wi-Fi or outside their houses, they cannot access the robot. So there is more security function about it on it.
We have a question from YouTube. How much weight can the scissor lift hold?
For now, it's only support about like 2 or 3 kilograms. But since it's a pretty early prototyping, and I hope I can increase the weight a little bit more.
Great. Do we have any other questions from the group?
I do. Firstly, again, I applaud you for attempting a live demonstration. Every single one of us, we have been there. As soon as you turn on the camera, as soon as there are people watching, what you're expecting and has worked 1,000 times before stops working. I fully believe you if you tell me that 5 minutes before it was working and doing exactly what you were telling it to. So you were using image segmentation, weren't you? You experimented with that a while, my understanding.
I'm using the Jetson Nano to do the image segmentation. That was a previous vision. Right now, I'm using a depth camera because since the segmentation, it takes too long to regularize to do the objects the depth the obstacle detection. So for now, I'm switching to the depth camera, and I hope I can increase the time to processing the image. For the segmentation, I just using simple simple AI segmentation skill to label the floor, and I put a lot of data on it to train the program.
You say simple, but successfully implementing your own image segmentation deep learning network embedded on your robot is a very impressive achievement. That's something you should really be proud of. And then after all of that hard work, then deciding it's not good enough and abandoning it to go down a different route. I really respect that as well. This is a fantastic project.
We had another question on YouTube. What kind of computer are you using on board the robot?
On board is a Jetson Nano with 4 GB memory.
Okay. When you say you mean like the Jetson Nano?
Yes.
Gotcha. All right. I think that's all the questions. Thank you very much for your presentation. Fantastic job.
Thank you. Have a good day. Have a good weekend.
All right. Next up, we have Sabine sharing their presentation on swarms for people.
Hi, everyone. Great, thanks very much for the invitation. Today, I wanted to tell you about my lab's work engineering swarms across scales from nanoparticles for cancer treatment to larger robots, and also our push to get these robots out of the lab into real-world environments. So as a swarm engineer, my source of inspiration is these flocks of birds. If you look at these birds, they can do beautiful, complex dances in the skies. And there's many features that are interesting for real-world applications. So for example, if you keep adding birds to the flock can continue to operate, so it can scale to huge numbers. If a bird falls to the ground, the whole flock doesn't crash, so they're robust to individual failure. And together they can do more than the sum of their parts. For example, these birds might be better at avoiding predators. Now, what's fascinating is that there's no leader in this flock of birds telling every bird what to do. These dances emerge from every bird reacting to their local environment, following maybe a set of rules, simple set of rules. And those reactions give rise to these dances in the sky. And actually, this is something that we called self-organization. We see examples of self-organization of swarming everywhere in nature around us, whether it's ants that create trails to your picnic table, or bees as they make decisions about their next nest site, or our ability to grow fully functioning human beings from just a couple cells. Now, the challenge as a swarm engineer is very often we have a group behavior we want to achieve. We want to do collective motion, optimization of trails. We want to do decision-making or consensus formation, the growth of structures, which is called morphogenesis. But we don't know the rules. We don't know how to design those agents and their local interactions with their environment. And that's what swarm engineers do. We try to crack that puzzle. So typically in my team, we use two methods. One is to use bioinspiration. If biologists have studied these systems, we can use the rules from biology and adapt them and simplify them so that they're useful in engineered solutions on robots. And the other angle we can use is exploration, which basically means guessing the rules or guessing the design of these robots. And that can be done with, someone behind a computer guessing, but it could also be done more thoroughly using machine learning so that we can automatically discover rules that give rise to desired swarm behaviors. So in the case of bioinspiration, if you have a set of rules, for example, we have rules that give flocking-like behaviors, you can put that on flying robots, throw them in the air, and then you can see it's very messy, but over time, you get these circular patterns that emerge. And this is work that I did during my PhD. So I'm behind the camera here, and I'm the one who programmed these robots to give rise to these dances in the sky. And, when I was looking at this as a PhD student, I thought, this is really exciting. We got to go and fly these robots, but there were only 10 robots. And in my mind, swarms needed to work in much larger numbers. And so I spent some time in a laboratory in Boston that made nanoparticles. And I'm going to do a bit of a dive into the nano and the micro world, but don't worry, I'll come back to the robots. The reason nanoparticles are interesting is because their tiny, tiny size makes them useful vehicles to deliver drugs into tumor tissue because they leak out of the vessels into certain types of tumors. And these particles work in the 10 to the power 13. So that's a huge number that you can start to get excited about as a swarm engineer. But on top of that, these nanoparticles, you can change their size, you can change their materials, you could change their shape, you could change their charge. Some of these particles were made of materials that were energy receptive, so you could zap them with light or magnetic fields and you could activate them. Or you could decorate these particles with molecules that would bind on receptors on certain cancer cells, and that would allow them to target certain cancer cells. You could also load them with drugs that they could release in a more or less focused way. And so I think what's interesting is, although they're not robots, you have many abilities in the design of these particles that changes the behavior of the particle. And so, depending on the size, on the shape, on the coating, on the material, these particles, when you inject 10 to the power 13, are going to behave in very different ways. And so we spent a lot of time thinking about how you turn those knobs on the design of those particles and how that gives rise to different distributions in tumors. And for example, just making particles more sticky or just making particles a little bit slower would cause them to all stick to the same cancer cells they encountered and would prevent them from going deep into the tumor tissues. And so this is just to show that some of the models that we've built, but I won't go into this, but more and more increasingly, we're able to create realistic models of where these nanoparticles are going. And you can see that these little nanobots are going and sticking to these different cancer cells. And we can see which ones they stick to. We can actually look at this under the microscope. So here you're looking at real nanoparticles in green and blue, sticking to little particles in red, which are pretending to be cells and little tumors on a chip. So we're able to wrap our head around how these nanoparticles work in those large numbers, depending on how you design them. So again, what does this collective behavior do? And there we're able to basically come up with tumor scenarios, grow virtual tumors, cut those virtual tumors up and try to design the right treatment for those tumors and come up with an optimal nanoparticle using machine learning so that we can basically quickly iterate on nanoparticle designs using some of the concepts that we have from swarm engineering. Now, some of the things that we help that we were interested in doing is that the game that what you saw before is a simulation. That was just me in a lab thinking about this for a couple of years. But actually what we did is we designed a game to crowdsource the design of these nanoparticles. And in that game, what we allowed the players to do was to basically encounter these tumor cells, healthy cells. You could change the dosage of these nanoparticles and the times they were injected at. You could combine nanoparticles. You could have particles with different sizes, and that would change how fast they would move in the tumor environment. Sorry. You could have cells that had receptors on their surface, and some of these particles would stick to those receptors with certain strengths. And you could load those particles with materials that they could release in a more or less controlled fashion. And then you could have particles that self-assembled, stuck to each other, or disassembled, and that changed how fast the particles moved or didn't move in their environment. So actually, as a roboticist, you start seeing that these particles could sense their environment, they could act on their environment by releasing something. That thing they released could trigger another nanoparticle, so they could communicate. And although they couldn't go left or right like the flying robots that I showed you before, they could slow down or speed up. And that gave rise to lots of interesting collective behaviors that were a little bit more swarmy at the nanoscale. So this is an example of the game that we designed, where people could go and design these nanoparticles, inject them, and look at what all those particles were doing and improve the design so that they could better treat those tumors. And we also played that game to come up with more swarmy behaviors. So for example, this is a rule set for the particles where you're able to create trails inspired directly from the way ants create trails to your picnic table. And so this is just an example of some of the swarmy things that we can do at the nanoscale. Now, one of the challenges that we have at those tiny scales is that to engineer the particle with that right design takes a chemist. It takes an expert, and usually it takes many years to make the right particle for a given scenario, even though in simulation we can test loads of things quite rapidly. And so we thought if we want to engineer nanoparticles or microparticles or cells or bacteria, we need a better playground to start thinking about their collective behavior. And so we designed this robot called the DOME for Dynamic Optical Microenvironment. And this DOME allows us to project little pixels, and there's thousands of these pixels that we can control. And every pixel projects at the size of the cell. And then what we can do is all based on Raspberry Pis, all open source. You can build this yourself if you're interested. It would cost you about £700. So you can project things on our microswarms, see what happens with a Raspberry Pi camera, and then basically close the loop so you're continuously interacting with these microsystems. And so here what I wanted to show you is just a video of this dome in action. So here you see little algae. They're called volvox. They're smaller than a millimeter. And these little algae were pretending that they're communicating by projecting little communication halos around them. So you can see basically this blue propagate through this network of algae. And so this is an example of communication implemented using our dome. Here's an example of volvox depositing light trails, a little bit like ants would deposit chemical trails in the environment. And you can see these volvox then, here's one of them, interact with those light trails by stopping. And you can see motion control. So we're basically zapping these little algae and they can stop. So this is an example of little microsystems where we can control their communication, their ability to interact through the environment, and their motion itself. And so we're hoping that this serves us as a good playground to design new types of microswarms that we think could be useful for things like treating tumors or treating wounds, or indeed treating things like biofilms or infections, because all of those systems at the nano and the microscale work in those very huge numbers. They'll work in the millions, they'll work in the tens of millions and beyond, depending on what system you're looking at. So that dive into the nano micro world was interesting because it also made me think differently about robots. So when you think of robots planting seeds in a farm, you might think of a lawnmower type robot or tractor robot that goes and zigzags through that farm field and plants the seeds in a very sequential way. But if you think in a way similar to the nano micro robot world, well, what if you had 100,000 little robot seeds that could buzz around that environment and plant themselves and would have the nutrients that it needs. They would biodegrade, and then they would basically just be left in the environment with everything that seed needed to grow. And I just want to comment that it's not a completely crazy idea to think of robots that are larger in this way. So here what you see is 100 little kilobots. We have 1,000 of them in our lab. They're little coin-sized robots. They have 2 vibrating motors to control their motion. They can communicate within 10 centimeters with their neighbors, and they can sense their environment through LEDs. And here what you're seeing is the nanoparticle algorithm I showed you before that creates trails. And all that's happening is we're releasing robots. These are real robots. They're moving randomly, and then they find something and they grow a trail. And this is really, really simple. Random motion, simple local interactions would work theoretically at the nano and the micro scale, but also works at robots without any calibration and any cleverness on the robots. Here, what you're seeing is 400 of our kilobots. And here they're changing between blue and red. Blue is the better decision. So we're trying to have this swarm reach the same color, blue. And they start, let's just wait for the experiment to restart. They start blue and red. It's going to start, here we go, blue and red. And then over time, they converge to blue, which is what we want them to do. And this is inspired from how honeybees make decisions. But here, what's interesting is that it's random motion, simple interactions. And yet at the level of the swarm, you're able to converge to a decision. Again, simple behaviors. And here what you're seeing is robots that are growing into shapes, and they have no plan of the shapes to form. There's 350 of these. These are real robots in the lab again. And what's interesting is they exchange little chemical signals between each other through wireless communication, and that generates spots on this sort of little organism. And these spots are actually, they're rules directly taken from Alan Turing about how animals generate spots in their fur or stripes in their fur. And you can basically, based on these spots, grow limb-like structures on this structure, and it's all self-organized. So these shapes grow, and you can chop elements of that shape off and they'll regrow, or you can split that swarm and it'll self-heal. And again, random motion, simple interactions, just very, very basic things that if you have enough robots give rise to interesting collective behaviors. And here's just for your, for the sake of it, another example of these robots organizing into shapes. And in this case, they're doing that based on projections on the robot swarm. So here you can see a line, a circle, an arrow, and unlike before where the shapes were packed, which uses a lot of robot material, these shapes just use the edge so that we can make bigger structures. And I actually think this has a lot of potential in the world of construction. Imagine if you could project a structure and then your robots would go ahead and build it. And like swarms in general, it's all dynamic. So if your shape changes, say you have this blinking eye, that swarm is going to adapt, because all of this is very much based on reacting to the environment around the robots. So as we think of these robots that work in large numbers, we need to think about a different way of designing them. And so you can imagine if you had to, cover that field with a bunch of robots for sensing or for farming or whatever application, you can make robots that sort of hop over an area. And what's interesting is you don't need that many hops to cover quite a large area, but you would need many robots. And so we've started thinking, well, actually, if we're going to build loads of robots, we need these robots to look very different. And maybe these robots need to be fully biodegradable. Maybe we would print them, load their energy, for example, if they're jumpers, by just curling them, basically loading the mechanical energy in them. You could paint them with smart paint so they change color. And if they were even powered by the environment, so it rains and that basically triggers these jumps, then you start to get things that are a little bit more sustainable and more mass producible. Okay, so that was a bit of the wacky world, the bio-inspired world. We do some very concrete robotics that are very closer to what the real world might like. And a lot of that is done using machine learning. So here what you're seeing is a swarm of XPucks. We call this the teraflop swarm because they've got loads of computation on board. They each have a GPU. And these robots in 15 minutes learn how to push the frisbee from the center of the arena to the right of the arena. Now, what's interesting is we haven't told the robots how to do that. That's fully learned on board each individual robot's GPU. And you can see it starts a little bit not great at doing it, but over time, 15 minutes, and they're able to do this. And this didn't require any external computation. So that could be interesting if you're putting it in a new environment for them to be able to learn these things on the go. And the thing that we learn is a structure called a behavior tree. So we don't do, big neural networks, because even though we have done that in the past, we don't easily understand them. And so the advantage of these behavior trees is that some of you who might be from the gaming industry might recognize them. They're human readable. So we can, at the end of the learning process, basically peer into what our robot has learned and read this behavior tree and get a sense for what the robot was doing. And then we have tools to sort of augment our understanding so that we can understand what behavior it was running at what time. And we think this is important if we are going to get these robots into the real world. So overall, I feel like we have many ways of designing algorithms now. We have many ways of designing hardware. There you saw just a couple examples of the hardware that we've designed. And I think it's the right time now to start thinking about how we get these swarms to people. And so to figure this out, I think we need to ask people. And so we designed an escape room called Swarm Escape before COVID, when we were allowed to lock people into spaces, and people would come by and it would take them 40 minutes to crack the puzzles and escape from the escape room. But in the process, they learned about swarm robotics, and then they could tell us where they thought swarm robotics would be useful in terms of the benefits for society versus the risks for society. And you can see examples like cleaning the ocean of plastic, construction, inspection of infrastructure, monitoring the environment, and some that are maybe not as high value to society. We also do a lot of science communication through two charities that we co-run, robohub.org and aihub.org. And then we do more specific use case studies. So we spoke with users who work in logistics, warehouses. We spoke with potential users who do bridge inspection. We spoke to users who do firefighting. And we asked them all if they thought swarms would be useful for them. And actually what was interesting is it didn't give rise to a completely science fiction discussion. No one actually went into science fiction. And many of them felt there were tasks at their current job that they needed help with, specific areas where there was an unmet need. And the other thing that was interesting was that they were open to swarms if we did it right. So there's always the but I want to make sure that it works, but I want to make sure that we can trust it. So I think I was really excited about these three separate types of conversations because everyone was open to it if we do it in a way that makes sense. And in particular, one area that we've started to look into more is the area of intralogistics. So intralogistics, think of warehouses, okay? If you think of Amazon or Ocado, they'll typically have a very big warehouse with lots of robots, but that is a very dedicated infrastructure. They'll have loads of infrastructure for that that's specific for the robots. The robots will have been designed for that type of environment, and that environment is slightly controlled. I think there's loads of areas where we could use many robot systems, but we can't because there's no out-of-the-box solution. So you can think of, a food bank, you can think of a pop-up warehouse, you can think of small retail, reconfigurable manufacturing. We spoke to museums, we spoke to loads of different types of people who would like robot solutions, but can't because they can't design, they don't have anything that's ready for them out of the box. And I actually think that's where swarms are quite fun. So, in the industrial world, you have your key performance indicators. You might think of your storage cost and speed, or your transport cost, or your inventory cost. And those are all important, but what swarms give you is the zeros. The zero scaling effort, the zero reconfiguration time, the zero setup time, the zero training, because everything is so reactive to the environment. And I just want to walk you through this example because I think it helps you think about what this means. So imagine you're designing a cloakroom. Well, you know, it's an event and you're a robot service, you provide a cloakroom for that event. Well, if it were a centralized solution, you would arrive with your robots, you would generate a full map of the environment of your cloakroom, and the user with their jacket would come to a central computer, and that central computer would say, okay, Bob, I'm going to allocate this robot to you, plan the trajectory of that robot, you would put your jacket on that robot, and then the central computer would plan where that robot needs to go and would memorize where your jacket is stored. So that's fine, it could work, but it requires a map, it requires your database to always be up to date, it requires the communication to work in a really seamless way, and it requires things that aren't predictable to not happen. If this were a swarm, I think the way this cloakroom would work is you would design little lines on the floor, and that's the cloakroom, so no map needed. The user would arrive with a little Bluetooth phone app, and would say, okay, pick up my jacket. And the nearest robot would just come by and they would put their jacket in that robot and scan the QR code. And then that robot would just move around in the cloakroom environment, not planning where to go, depositing the jacket somewhere. And then when the user comes back, they would say, okay, I'm looking for jacket with QR code 10. And then that robots would all look around because there's lots of them, it's a swarm. And they would say, oh, I see jacket 10, exactly like humans do actually. And they would go and pick it up and bring it back to the user. So in that context, there's no planning, there's no central control, there's no need for a map. And actually that user could have just jumped in and picked up their jacket themselves, and that would have worked okay. So I think we're at a stage where we can start to get these swarms in reality, even in an industrial setting. And to do this, we designed a new robot platform called the DOTS for Distributed Organization and Transport. They're quite fancy, much fancier than those little coin robots. They're this big, they've got really good computation, they're super fast, 8 hours of battery life, 4 cameras, laser time of flight, range sensors. We've got pretty good simulations of them in 3D. This is using Gazebo. And here's just the first demo of us translating these types of behaviors to the robots. We haven't done any refinement of this yet, but it's literally the same code in the simulation world and in the real robots, so that we can start to build sort of a digital twin and a test bed that allows us to wrap our head around how to design these behaviors. And this was part of a big international competition. And increasingly, we're trying to figure out what is it the user would use, you know, either the cloakroom, the user, or the person with the jacket. What is it that they want on their screen so that they can have confidence that the system is working? I also wanted to mention a couple other things that we're doing in the real world. So this was a month ago where we have another new swarm. These are also Raspberry Pi based robots, kind of screens on wheels. These robots, we've got 100 of them. We use them in social settings, so sort of social robots for social humans. And in this case, we were asking a crowd of people at the mall what they thought we should do to fight climate change. And what was fun is it gets people talking. They can see the opinions of others before them. So these robots are like physical avatars that make your opinions travel. So that you can, you know, if you're shy, you can share your opinion, you can sort of see what others thought before you. And it also led to loads of discussion. So that's another angle, is how can robots help humans reach decisions and brainstorm and be creative? And then we have another project.
Real quick, Sabine, we've got about 9 minutes left, so we do want to leave time for questions. So.
Okay, yeah, I'm almost done.
Thank you.
Almost done. Thanks. So this is another project looking at how we can use swarms for fire monitoring and mitigation and aid delivery using very large swarms with high payload. And again, there we're thinking about how we design digital twins so that we can create a swarm operator who has confidence in interacting with these swarms. So I think there's many areas where these swarms make sense, but we'll need to make these trustworthy. And so these are just questions that we have. We don't yet have answers about how to make these trustworthy. But it's worth asking these questions now, as it's still early days in their deployment into the real world. So this is the result of very cross-disciplinary work. And and also really led by the PhD students and postdocs in my laboratory. I tried to put their names of their papers at the bottom, but many of them have come from loads of different backgrounds. And just thank you. I'd be happy to take some questions.
All right, thank you very much for that. Sorry, let me.
While Chris brings up the questions, I just want to say that was absolutely fascinating. That dome is something I've never seen before, and for £700 it's a steal. Chris is giving the same reaction. That was jaw-dropping. And then the cloakroom example is the first time I've actually heard and understood a viable use case where I can see why swarm robots would be more effective in the real world than a non-swarm system. And that really is fascinating and eye-opening too. So thank you very much. Chris, back to you.
Yeah, lots of comments on the dome from the YouTube stream. They seem to like that. We had one question. You have lots of demos of the swarms working in rooms with like trackers and stuff. Is this something that can be applied in the real world outside, with chaotic elements?
I think they can. Yeah, I think they can, because they don't rely on anything else than themselves. So I think we're at a stage in robotics where we can also give more intelligence to the individual robots. So their ability to perceive their environment locally. We saw some examples earlier on. Their ability to communicate quite efficiently with their environment. Now we have 5G on the horizon. I think we're starting to get enough intelligence that this combination of intelligence plus the clever rules that we've been thinking of in swarming for a long time now actually makes this a reasonable prospect. And I think there's also sort of, the reason we use the cloakroom is it's not a high risk scenario. And so I could see people just going for it and adopting it. And I would test this as soon as it's ready. So the robots that we're designing, I think we could actually test them in this setting in the real world. And I think we should sort of play around with these low risk areas while we're developing confidence in how to deploy them. So yeah, I believe in it.
Great. Somewhat related question. How robust are these robots, and if there's a defective robot or one not behaving correctly, how disruptive is that to the swarm? That's
a great question. So we keep saying swarms are robust because they're all the same and there's no single point of failure. And in theory, you could remove one of these robots or two or three and the system should still operate. The reality is much more complicated. And so there's a couple things that we're looking at. For example, if one fails in a bad way, they could influence the other robots and not allow them to explore their environment. So it's much more complicated than that. So we have a couple projects now doing two things. One is to sort of prevent them from failing, and the other is to figure out how you detect them from failing, a sort of an immune system for the swarm, where because they're all behaving the same, they should be able to look at their neighborhood and say, you're acting funny. And so we're trying to find metrics basically that give a sense of self for the swarm so that they can be mindful of that and fix for robots that are faulty. Then there's a whole cybersecurity element as well. So that 10-point checklist are actually all things you need to figure out if you actually do want to be robust.
Great. Going back to the dome, somebody was asking if they wanted to do some kind of project like this. Do you have recommendations for hardware? Just things to think about.
Yeah, so Anna built the dome during her PhD. So she just handed in, and she should have her Viva really soon. And now she's adapting the dome to make like a wearable version of it for biomedical applications. She started, I think the only advice I have is to go for it. There's a lot of off-the-shelf components that you can use. And she has an image in her PhD of what the first version looked like. And it was nothing like the last version. But the only reason she got to the last version is because she did that first and second and third and fourth version. So, 3D printing, Raspberry Pis, anything you can get off the shelf. There was one component we got from a maker that was a board, the interface, a really cool, this tiny projector that we have. And that stopped being made. So she had to go to like technicians and figure out how we reverse engineer some of that. So, there's lots of stuff out there. I think you'd be surprised at how much you can do.
Very cool. I guess a comment or asking for clarification. Going back to the the defective swarm bot. We're looking at system identification or state estimation for points of failure. Is that accurate?
Exactly. So one element is just the ID, the identification that you're part of the swarm and not some nefarious external actor. But the other aspect is assessment based on what you know from the past is a normal behavior. So it could be based on what you know from the past is your normal behavior as a robot, or it could be based on what your neighboring agents are doing, which could also give you a measure of how good you're performing. And then there's also the swarm behavior as a whole. Like if you're trying to deliver boxes, there's a thing you can measure and you can figure out if that's going in the right direction or not. A little bit like a fever in the body, right? If there's something bubbling up that's just not going right, that's also a marker that things need to be checked.
I like that immune system analogy. Kind of makes sense. Do we have other questions from the committee or from participants? All right, I think that is all the questions we have for your presentation. Thank you very much. That was very interesting. Okay, we have a 10-minute break scheduled. Let participants in the committee rest. We'll be back at 3:45 EDT. That is about 10 minutes from now. right, I think we're ready to get started again. Next up, we have Calvin, right? We have Calvin with BeBOT presenting on Bernstein Polynomial Toolkit for optimal trajectory generation. Take it away.
Well, thank you. My name is Kelvin, and today we're going to talk about BeBOT, which is the Bernstein Polynomial Toolkit for optimal trajectory generation. Here's a quick outline. We'll go over a short background, followed by optimal motion planning. Then we'll talk about Bernstein polynomials, and we'll finish up with some examples. So the price and size of autonomous vehicles has been decreasing, making systems comprised of multiple autonomous agents viable. Now, multiple agents can outperform and are more robust than single agents acting alone. This has led to a huge demand in computationally efficient trajectory generation algorithms for multiple autonomous vehicles. So some of the main challenges in trajectory generation is complex problems such as cluttered environments or robots collaborating with each other. Also, we care about safety guarantees. Of course, we don't want to have an autonomous vehicle drive into other vehicles on the road. And then finally, we care about computational efficiency so that our robots can react to constantly changing environments. So motion planning can be split into two common ways of solving. You can either generate paths or you can generate trajectories. Now, a path is akin to what you would see on a route planner from some mapping app. So it's just a path for you to follow. While a trajectory will also tell you exactly what speed you should be going at certain points along the path. So in a nutshell, the trajectories will have slightly more information to them than a path will. And this is why we like to use trajectories as opposed to path planning. Now, there are many, many different unique solutions out there, such as the older tried and true algorithms like A-star, RRT, or PRM. And then there are, of course, the more modern algorithms such as CHOMP, TrajOpt, or GPMP2. And so for this work, we would like to make use of optimal control theory. Now, unfortunately, many optimal control problems are actually impossible to solve by hand. Therefore, we choose to convert the optimal control problem into a nonlinear programming problem, which can then be solved using off-the-shelf planners such as IPOpt, MATLAB's fmincon, or SciPy's Minimize. And in order to do that, we're going to make use of Bernstein polynomials. So what are Bernstein polynomials? Well, first of all, they are also commonly referred to as Bezier curves. And if you've ever worked with a vector graphics program, for example, Inkscape, you may have worked with these before. Essentially, you can intuitively change the shape of your curve by moving around certain control points. So the Bernstein polynomials were originally developed by Sergei Bernstein as a proof for the Weierstrass theorem, but then later they gained a lot more popularity after de Castelja and Bezier, which were two French automotive engineers, after they started using them for designing vehicle contours. So the Bernstein polynomial, which is shown right here in blue, is defined by this equation right here. And so we have the control points, which is this vector here, and the control points are each point here, which define the shape of this polynomial, and then also multiplied by the Bernstein basis, which is shown right here. So some of the reasons we like to use Bernstein polynomials are their useful geometric properties. So first of all, the Bernstein coefficients or control points, the convex hull that's defined by those points will always enclose the polynomial. And so we can see here in the one-dimensional case that the polynomial is in fact in between these values. We can also see a different convex hull drawn around the polynomial here. And once again, we know that the polynomial will lie within those points. We also know that the Bernstein polynomial will pass through its endpoints here and here. And similarly, we can even take the derivative and higher order derivatives of the polynomial and get more important values by just looking at the endpoints, which is also a very useful feature of them. The de Castelja algorithm is a very efficient and robust algorithm which can both be used to evaluate a Bernstein polynomial, and it can also be used to split a Bernstein polynomial into two separate polynomials. So we can see right here where the Bernstein polynomial is split. And similarly here, it has been split into two in 2 dimensions. And then right here, we have split it at 3 different places. Finally, the degree elevation property of Bernstein polynomials is useful because, first of all, we can compute a degree elevation matrix offline, which allows for very efficient online computation. And as we increase the order of the polynomial, we start to converge to the actual polynomial, which means that we can get more accurate approximations of the minimum and maximum values of a Bernstein polynomial. Now, unfortunately, the control points do converge slowly to the polynomial. However, that's not too big of a deal because we can justify that with these useful geometric features. So I, along with the other members of the University of Iowa Cooperative Autonomous Systems Lab, have developed the BeBOT library, or Bernstein-Bezier Optimal Trajectories. Now, this library is available in both the Python and MATLAB programming languages, and you can find more information about that on GitHub at the link shown in the bottom right-hand corner. So let's go over a couple examples of what we can do with BeBOT. So right here, we are showing a vehicle going from point A to point B in the quickest way possible. So without doing any degree elevation whatsoever, we can see this blue trajectory going from A to B and taking a very conservative, slower path from the starting position to the final position. Now, as we slowly increase the order of the Bernstein approximation, we start to get more and more efficient routes. And finally, if we do a degree elevation by 100, we're able to get a very, very efficient route from A to B around these obstacles. The catch with getting a more efficient route is you do have to spend a little bit more computation. So like all things in engineering, there is a trade-off there. We can also generate trajectories for multiple autonomous vehicles. In this case, we generated trajectories for 103 aerial vehicles that start on the ground and fly up to an altitude of 30 meters. We also placed an obstacle at an altitude of 15 meters in order to show that we can indeed avoid obstacles as well. In this example, we did also impose a minimum safe distance of 0.9, which means we don't want the vehicles flying any closer than 0.9 meters together. Now we can take this example and blow it all the way up to a swarm of 1,000 aerial vehicles. And traditionally, this is a very hard problem to solve because it has so many dimensions to it. And oftentimes in these types of optimization problems, you'll run into something that we know as the curse of dimensionality. And so as you increase the dimensions of the problem, your problem gets exponentially more challenging to solve. And so this is a really great example of what we can do with these additional computational efficiencies afforded by BeBOT. And of course, we did validate everything with physical flight tests, which we can see here. We have 3 drones in the CAS lab that fly from their initial positions, and they will exchange positions at some final position over here. In the bottom left-hand corner, we can see the simulation of what's going on in real time, where these bars represent the actual physical location of the drones, and then the blue circles represent the desired position for the drone to follow. Now, on the right over here, we also have an example of an uncertain target that is moving, and we are tracking that target with three UAVs. And the nice thing about this is they can react to the vehicle changing position because, of course, most vehicles that you'd be tracking would be moving in some kind of uncertain way. So finally, I would like to take this time to thank the organizers of this. I am very happy that I was able to present here, and thank you all for watching this. And now I would like to take this time to open up to any questions.
Thank you very much for presenting. Yeah, this is really interesting. I feel like in some ways it relates pretty well to the previous presentation on swarms. This is a more analytic approach rather than like machine learning. Yeah.
Yeah.
We have a lot of comments about math in the chat.
I'm sure. Yep.
Yeah. Mark Emerton commented he tried to tackle a problem similar to this and found it very difficult.
You are correct. It is challenging. Yep.
Hi. Yeah. So can I add then on that point? Because, like, again, as with many people, somewhat afraid of the mathematics. When you're using, if you were to go about using the Python or the MATLAB interface, to what extent does that then take away the problem of the mathematics? Is this something that you could easily then implement in a system? Is this something you could integrate with robots without having to have that in-depth knowledge?
Yep. So the library has a bunch of examples which people can take and run with on their own. However, the core purpose of the library as it is right now is specifically just a transcription method, which will convert the optimal control problem into a nonlinear programming problem. And so if you're trying to do something a little niche, this is a very general approach, which is kind of nice because it does lend itself to several different types of problems. In the future, though, we are planning on integrating this with ROS, and as the days go on, we are working on getting a nice ROS package that other folks will be able to very easily plug and play in order to use these methods. Not dissimilar to some of the most popular ROS packages like the navigation stack.
Yeah, I can see this having same value in the same way that, you know, A-star path planning has value in it.
Yeah.
Yeah, certainly. Fantastic work.
Yeah, thank you.
Yeah. So we do have some questions now. In your algorithm, how do the drones know to avoid each other? How do these trajectories interact with each other, I guess?
So we have a couple different ways of doing that. One is called temporal separation, and the other is called spatial separation. So I'll skip the spatial separation because that is an iterative algorithm. And so it doesn't lend itself very well to running through an optimizer. It's more of a validation step. But in order to avoid each other, we can subtract the two Bernstein polynomials from each other. And by doing that, you're able to get a distance between the two polynomials at any point in time. And by checking that distance at any point in time, all we really need to do is find the minimum value of that entire polynomial. And so then as long as the minimum of that polynomial is greater than some threshold, then we're able to avoid obstacles and other drones. Now, if we want to do a static obstacle, we just treat the static obstacle like a Bernstein polynomial, except where all of the control points are all at the same point. And so that, of course, looks just like a vehicle that isn't moving. And so again, we can do that temporal separation check in order to efficiently figure that out.
Great. we have a question about use cases. So like, is there demand for these kind of algorithms without like deep learning or some of the other techniques you might use to
Yeah, so the nice thing about this more traditional approach is that it's explainable. So a lot of machine learning based approaches aren't necessarily explainable. And what we can do is have a tiered framework, and we can have these safety guarantees at every single level of said tiered framework. So we guarantee everything works on the motion planning side, and then we can use something, for example, Lyapunov theory, in order to guarantee that a trajectory tracking controller would perfectly follow said trajectories.
Great. That is all the time we have for questions. Thank you so much for presenting. That was really interesting.
Yeah, thank you guys for watching.
All right, next we have human mode robotics.
Hello, can you hear me okay?
Yep, we can hear you.
Okay, awesome. Well, thank you guys for the organizers of Reddit Robotics Showcase for the invite. I'm William Kerber, CEO of Human Mode. I'm here with some of my team, Jonathan Turner, robotics engineer, Mehul Kumar, AI engineer, Mitch Lane, who works in marketing, Chi, who is my co-founder and wife, and we have a couple of members that are traveling. They weren't able to be here, but I want to say hi to Bao and Jay, who are out there. Human mode, we do a lot with integrating robotics with VR, and that kind of comes from our VR roots. We started working in VR software and then got into what I would consider bidirectional haptic VR interfaces. So we started working on gloves and vests and things of that nature, helmets, where naturally you would have haptics in VR, but just kind of my interest in closing the loop between the virtual and the physical. What we wanted to do was make it so that they were bidirectional, so that if I like impacted a person wearing the suit, then like my avatar would get hit, and so on and so forth. So kind of closing the loop. And as we were doing just a number of these experiences, we had like maybe 6 experiments, I think, up in the first year and a half. Somehow it kind of came on this idea of, what if we just flip it inside out, right? What if instead of working on virtual avatars, we were working on physical? And so we started applying the VR technology that we were working on to physical avatar, and that resulted in something we called the mech suit, and then our first robot, the Gemini 0.1, and then we just kind of went full steam into robotics and haven't really looked back since. I have a short video that kind of shows some of the stuff we've done real quick, and then we can come back to a presentation to kind of describe it a little better. God, it's got my ear.
All right, whenever you're ready.
Okay. My name is William Kerber. I'm the CEO of Human Mode. Human Mode is a small research company that I started at the end of 2017 to focus on futuristic technologies like AI, virtual reality, and robotics.
The mech suit is a full-body robotic control suit. Its patent-pending design allows you to control remote machines using your natural human motion. When you're wearing the suit, the robot is an extension of yourself. You can hear what it hears and see what it sees. Together, the mech suit and Gemini series robots will help us explore applications for semi-autonomous robots.
My favorite part about technology is the invention aspect. It's staring at the blank sheet. And that's why invention is such a huge part of Human Mode's DNA.
Meet Gemini 0.1, and while he is in the early stages and phases of robotic life, creators say he's got a lot of potential.
Cool.
Awesome. That was a little jittery, so
Oh,
we'll
sorry.
add a link to the YouTube video at the end.
Okay.
But I think that got the idea across still.
Push through. Okay, so yeah, we were founded 3 years ago. We started the robotics program after we finished our haptic interface research in 2018. And then we basically started iterating. So if you think about the robots, really what we're really just doing is solving individual problems with each one of them. The goal really is multi-use robots, not so much just a narrowly focused robot like a robot lawnmower or something of that nature. We want to make some that are adaptable and programmable, and that have some generalized intelligence, so some simple intelligence. Each project is basically meant to solve a problem. So we tackled strength, for example, with the Gemini 0.3. That's a real hard problem with robots in particular. I mean, we all know, anyone who's tried, trying to compete with the human body is a really humbling experience, just in terms of agility, especially per pound. Everything you do just keeps adding weight to the machine. So they're just iterative projects that need to be researched. So we have a multidiscipline team. Like I mentioned, our goals are really not so much narrowly focused robots, but more complex robotics that merge some synthetic intelligence with them to for one, keep people out of harm's way, but also potentially be good companions and so on and so forth. Can you move on to the next? Cool. As I mentioned, we basically divide research into two categories. One is chassis design. The other one is the synthetic intelligence or the brain. So we divide these into two separate projects with the goal of merging them back eventually. In particular, VR control and the mech suit are helpful because I feel like if you can't drive a robot using human intelligence and human agility, well, you're very unlikely to do it well if you're using a subpar AI, for example. So we need to really start by driving it with by mimicking our own human ability. So we started there. Next slide. Yeah, again, these are the projects. The first one was basically just as a target for the mech suit. It doesn't maneuver very fast. The second one, we really need to become untethered. The third one, we realized that robots in particular, agility and strength, it's a real issue, and designing good joint structures and things is a difficult problem. If they're going to be useful robots, I mean, they have to be able to lift human proportional material, and so we put some focus on that, and we do learn from them. They don't necessarily solve the problem 100%. We don't necessarily get exactly, but we get steps basically. And then again, the entity basically, we have a plan where we basically iteratively work into that. We did a lot with vision through the first 6 months, and we're kind of moving on from vision now. And then we have a quadruped in progress. It's also to test a particular theory with regard to speed. So, we want to be able to better accommodate the human controller. Like if we're maneuvering in VR, there's going to be some latency between how quickly the robot can react and how quickly we can. And so we're trying to narrow that gap through this project. Here's an example of what you see from a VR integration standpoint when you're on the other end of controlling the machine. So here's an example controlling the Gemini 0.3. Okay, that's good.
Then all you want to show?
Yeah.
Okay.
And then, I wanted to mention we are enthusiasts, robot enthusiasts of every size and shape. We've been building these out of our garage essentially, and in an office with cubes. It's not really the most ideal environment. So this year, we made an investment to actually build a shop so we could start better fabrication. We just got our first CNC machine like last month. So we've been, using pretty primitive tools to try to accomplish these goals. And I think it's going to kind of give us a boost in terms of what we can do. So I'm looking forward to that. It's exciting. And I think that's it. If you guys have any questions, hopefully we can answer them.
All right, fantastic. Thank you. We do have some questions.
Okay.
First question from YouTube is your plan eventually to bring this to like industrial mobile robotic hardware, like manipulation on industrial platforms, things like that?
Not necessarily. I mean, I really just like to push the technology. Just some background for me, I was the core software developer and then later CIO of a company called Paycom. And I was there for 19 years, and it's really meticulous accounting software, basically. But I'm a futurist, and I'm also really just a fan of technology. And so during that, that career, I spent a lot of time researching machine learning and advancements in neural networks and just general advancements in robotics, and really wanted to see, what was possible in the realm. And so my goal is to just continue to progress, and as long as we're not hitting walls, I feel pretty good about that. So once we hit walls, I might reassess, but we haven't hit any yet. So I'm just going to continue to try to see how far we can push it in terms of general humanoid structures and better useful intelligence instead of just not just conversational AI, but actually better navigation and so on and so forth. So
great. So you guys have a lot of different technology that you're kind of working on simultaneously, hoping to reintegrate. What would you say is the most difficult part? You've got software, you've got hardware, you've got different kinds of manipulation. What's the biggest challenge for y'all right now?
I mean, all of it, I think is, I think they would agree, all of it. I mean, the body, in particular, like if you look at machines, you really want to build something capable in a humanoid form, aside from just, balance. And we're early in it, I mean, Boston Dynamics was at it for 2 decades, we're at like 2 years, but you have the obstacle of navigation in uncertain surroundings, but then just strength, as well, and agility. And I mean, the human body is really quite remarkable. I mean, we can spring suddenly, we can turn sideways, and just matching that in any useful format is really hard from a chassis design standpoint, to where you wouldn't just ask your 10-year-old niece to go help you instead, right? I mean, if you needed a robot to go get your mail, I mean, realistically, you would be like, you would not necessarily want to wait around for it. So we need advancement in that realm in order to really approach something that would be useful as an assistant, and break out of just narrowly focused robots. So that is difficult from an AI standpoint. I mean, there's clusters of useful algorithms, but in my opinion, most of the techniques are very top down, and they're basically it's through excessive pre-training, which isn't necessarily how things should learn in a raw environment. They should instead start with minimal information and then adapt. And that's kind of backwards. In a sense, it's like taking AI and putting it back into expert systems, right? I mean, we have all the benefits of neural networks and other AI techniques, and we just, pre-train and pre-train and pre-train until we have a very complex model, but that's not really how a child learns, for example. So really revisiting that, I think, is important. Yeah.
Thank you. That is the time we have for questions. Thank you very much for presenting your work.
Yeah, thank you. Appreciate it.
All right. Next up, we have Ammaar on last-minute delivery robots for residential buildings.
Hey, hi. We can watch the video first, and we can go to the Q&A.
All right. Do you want to share your screen?
Yeah, just a moment. No, is it visible?
We can see it. You may have to enable audio. You want to try it?
Hello, everyone. I hope you all are enjoying the event. I am Ammaar and I'm here to talk about
We lost the audio when you muted.
of robots making deliveries by now. Several companies are now. I am Ammaar Solkar and I'm here to talk about my project, which is last mile delivery robots for residential buildings. So, you must have seen or heard of robots making deliveries by now. Several companies are now making robots which are delivering food, groceries, packages, and a lot of stuff to our homes. But the thing is, these robots don't exactly cater to people living in apartment buildings. If you live in an apartment building, you would either have to go to the lobby to pick up the package or you're out of luck. Well, it doesn't have to be that way, and that is what my project is about. So I made a virtual robot using ROS and simulated it using Gazebo, a popular physics simulator. The functionality of the robot goes somewhat as follows. The robot is dropped outside the building or in some pre-specified area. Why this constraint, you might ask? Well, it's because it makes it easier for the robot to figure out where it is in the world. The robot is given the details of the delivery to be made, that is the building name, floor number, and the room number. The bot already has a map of the buildings and it gets it using the building name given to it. The bot calculates the path it will need to perform the delivery and gets on its way. The bot navigates through the lobby of the building and reaches the elevator. There, it sends a request to the elevator and waits for it. Once the elevator doors open, the robot gets in and sends the required floor number to the elevator. The elevator then takes the robot to its floor. Once the required floor is reached, the bot moves out and goes to the required door. It stops in front of the door, checks the number plate to verify if the door is the correct one, and if it is, it drops the package in front of the door. The package is now delivered. A picture can be taken and confirmation can be sent to the customer. The robot then goes back to the starting area it came from and waits there for the delivery van to pick it up for the next delivery. So let's talk a bit about what is required for the bot to be able to do this. The apartment building which is being targeted will have to be mapped once prior to running the deliveries. This will require a person to accompany a robot or a mapping device to map out the floors which have fundamentally distinct structures like floors and lobbies. These maps can then be reused for areas which have similar structure. For example, most floors will have the same structure, so it is not required to map all the floors, just all the unique ones. This will save time and money and make the process easier. Once the mapping is done, the building can then be eligible for autonomous deliveries. So whenever people see this project, the one thing that comes up is, okay, Ammaar, this sounds good, but how can we implement this in real life? How will the robot interact with the elevator? Well, let's consider two extreme ways we can do this. The first one would be to attach a manipulator or a robotic arm which is capable of pushing the buttons. But if the robot is to move around humans in cramped spaces like elevators, I personally don't like this method. The other end would be to have the buildings be fully IoT enabled, continually talking to the robot, taking the robot where it wants to go. Take for example, the robot comes to run a delivery. The robot says, "Hey elevator, take me to the 20th floor." The elevator goes, "Sure buddy, come on in," and waits for the robot to come in and moves to the 20th floor. This, in my mind, would be the ideal case, but we are not really there yet in terms of technology adoption. So, how do we implement this? Well, we can either wait for the technology to become mainstream and then start building these applications, or what we can do is start by retrofitting elevators to work with IoT, creating the demand for IoT enabled elevators and buildings, and pull the tech with us. Either way, it's going to be exciting because someone is going to figure it out and it will be really cool. And that is my presentation for today. If you want to learn more, you can check out my GitHub or LinkedIn. Thank you.
All right,
Hello.
thank you for your presentation. So what is your primary motivation for doing this project, right? This is for deliveries. Would this be like used by Amazon or something?
Yeah. So the first time I saw this, like we had a hackathon, a Smart India hackathon, and there was a problem statement there which required like Amazon had this problem statement that they wanted a system which can easily find places like navigation and indoor areas for deliveries. So I thought, okay, if this is not available, what do the current delivery robots do? So I started getting into that. Then I'm okay, this might be a cool idea. So that is why I did it, because I thought it'd be nice to have delivery robots like coming directly to homes instead of just like, you know, in suburban areas to the door of ground floor or just lobbies.
Yeah, absolutely. Would you say is the biggest challenge in working on this project, getting everything to work?
The biggest challenge would be to like get these robots to work with the elevators, because currently we don't actually, I don't think we actually have anything which can be easily used. So that would be the main challenge to solve, because if we have that done, the other thing can be done by software. It's not that like it is doable, but the most problematic thing would be to like interact with the elevators and doors if there are there in the environment.
Right. We have a question from YouTube. Does the robot know in advance where the apartment is, like what the layout is, how to get there, or does it have to find it?
So it would be easier to have the map of the building prior. So like we can have is a personnel from the company goes there, like they either take the robot or some mapping device like a camera hooked to a IMU or something, and map the device in beforehand. Like you go there, you map out the lobby, you map out 1 or 2 floor areas, map out the elevator, then you have a map, then you store it, and then you use it, because navigating in an unknown environment would be very difficult, like finding the places. So what we do is we create the maps and we store the locations we require, like in the map there was room 1, room 2, room 3, because the structure would be the same. So we know the coordinates we require, then we can do a better adjustment before the delivery if there is no obstacle or something. So yeah, in this one we need to have prior mapping.
Gotcha. All right, thank you. It's a great
you.
presentation. Last up, we have Miro presenting ExoMi.
Hi everyone, nice to be here. Greetings from Switzerland. I can share my screen with everyone. and then we can get going. Let's see. That works. Yes, like this. Great. Okay, cool. So today I'm presenting to you ExoMai, the 3D printed rover. Maybe this is, I introduce quickly Max and me. So Max is not here today, but together with him, I developed ExoMai. We were both at the time robotic trainees at the European Space Agency. We were working in the Netherlands until basically me last year and him till March. So now we're former robotic trainees, and that's why we also have to remove the ESA branding from the presentation. I now work at as a mechanical engineer at Syntegrity Engineering in Switzerland. Here we do contracting, and Max works in Augsburg at the rocket factory, building new launchers for Europe. We have to compete with SpaceX. So what is ExoMai? How did it get into this world? At ESA, every year there's an open day where a lot of people visit the site, they visit the lab. This is where we worked in the Planetary Robotics Lab. There's these big rovers that cost a lot of money, and you have a lot of kids that want to control something and have some kind of fun and see the world and see the world of robotics. So we wanted to build a rover that was cheap. Ideally, it should be able to be built by a lot of people. To allow this, it should be 3D printed, it should be friendly, so a young kid is happy to see it and is directly fascinated and puts a smile on their face. And since ESA is launching the ExoMars mission in 2022, we wanted also to build a rover that is not inspired by another rover, but of course by the ExoMars rover. And to reach more people and to have people build it, also it should be open source. So we went ahead in 2018. This is the first iteration you see here on the left. Wait, I need a pointer. You see here on the left, this is a ExoMars mock-up, ExoMars model, 1-to-1 scale, and here you see the first mini ExoMai rover. It was working. It was not working great. Okay, but it was a proof of concept, and then we managed to iterate on it. We added cuteness to the whole system. What we noticed as soon as we added this head, people started to notice it way more. They were taking pictures not of the big expensive rovers, but of this little thing, and this drew attention to the laboratory itself and to robotics, which was a great thing. As you see, there's still cables hanging around. It's not polished, but again, proof of concept was there. Then we basically went completely to the drawing board. We took what we learned from these first iterations and we made a completely new model. You see now all the cables are hidden. Everything is designed in a way that you don't need to screw it together awkwardly here. We simplified it drastically, and that you only need 3D printed parts and no ball bearings, for example. And this is the design we have right now. And suddenly it's done. Suddenly we have a design that can be pushed online and that can be shared with the world. And that's why I'm also here now today. Again, the evolution shows very well how this project has evolved. Now I mentioned similarities with ExoMars, and we took the most important design features. So the solar panel, for example, the locomotion system is also a triple bogie locomotion system. We have a drill mock-up on ExoMai. And finally, the wheel pattern is inspired by the ExoMars wheel pattern, wheel design. The ExoMars wheels are flexible, as you see here, but they are the ExoMai wheels are not flexible for simplicity reasons. Now some small specs. I like to say it's the size of a cat. That's the easiest explanation in terms of size. And usually, if you run it and you operate it, it can go for up to 4 to 5 hours. For example, on the open day, I think we had to change battery once in the middle of the day, and it was in use pretty much the whole time otherwise. To give you a quick system overview, As mentioned, the triple boogie. So the triple boogie, actually, for those that don't know it, it's the locomotion system of ESA, the preferred system. And it's actually different than the rocker boogie that is used on the NASA rover Perseverance, etc. Because what we have here is we have a simple beam on a pivot. And this is simply just a pivot bearing. So no actuation in this axis. And then you have a motor here, a motor here with the steering. And if you push up on the front wheel, for example, this gets pushed down. And so you always have the same forces actually acting on these two wheels. And you have the same across the back and the same across the other side. So you have 3 of these boogies, thus triple boogie. And you have somewhat equal forces on all 6 wheels with a very, very simple setup of just having 3 pivots. Why is this important to have these equal forces? This will allow you to climb over big obstacles with not so much force. And you will see later in the video of the performance in obstacle navigation. Each of the 6 wheels is actually actuated. So we have 6 driving motors. Each of the 6 wheels is steerable, which is also different compared to NASA rovers. So we can steer all 6 wheels. The cuteness can actually be customized. So you can actually exchange the head and the mouth. So even a very young child can already have fun with this robot. If you want to drive on flat surfaces, you can add wheel sleeves. These are now, in this case, printed out of TPU flexible material. This will allow you to not have the grousers and bump so much on the hardwood, for example. We have 2 switches for easy activation of the rover and also to turn off the motors just to have it safe. Looking inside, we paid a lot of attention to use only open, widely available hardware. So we didn't want to put a custom computer or anything like this in there. Instead, we put a Raspberry Pi with Raspberry Pi camera, off-the-shelf LiPo alarm. It all fits in there. The LiPo battery can actually be very easily pulled out. And what's also nice is the GPIO of the, what am I saying? The I/O of the Raspberry Pi, like the USB ports, the HDMI ports, can easily be accessed without any tools. This was very important. The 12 motors are actually controlled using a PWM servo head. Using this, we have up to 16 hardware PWM, which proved to be a very reliable solution because the Raspberry Pi is insufficiently in terms of software PWM. Performance is not working out in that regard. In the head, there is a camera hidden. We use the Raspberry Pi camera. It looks sneakily through the mouth of the XMI. And what's also important, with 2 DC-DC converters, converting the 11 volts from the LiPo down to 5 volts for the Raspberry Pi and around 6 volts for the servo motors. Having a look here, this is exactly what I just explained, and it's important maybe for other projects here. It was important for us to have these 2 separates because if the servo motors draw a higher current, the voltage could drop, and this caused the Raspberry Pi to crash, and that's why we had to use a second one also. Even if we could run the servos at 5 volts, it was still necessary to have a second one. Also the software, this is actually also one thing we're proud of, and that was one challenge is to have a software stack and software package that can be deployed on any kind of Raspberry Pi and on any kind of OS reliably, because we don't know if someone builds it with a Raspberry Pi 2 or Raspberry Pi 4 or in the future with Raspberry Pi 5. And it should still work on this Raspberry Pi. And actually we wanted to use ROS because it's good if the people learn ROS for obvious reasons. And using ROS on different Ubuntu versions is tricky, or using a specific version of ROS on various Ubuntu versions is tricky. So you always want one specific Ubuntu version with one specific ROS version, and installing a very specific Ubuntu version on a very specific Raspberry Pi doesn't always work. So we virtualize everything with Docker. We virtualize the Ubuntu environment, and in there we have a ROS environment running. And this actually shows to work very, very well. Also, they allowed very easy installation procedures because the people could just install Docker on the Raspberry Pi. The rover can be controlled, remote controlled at the moment using a gamepad very easily. But we also designed a web interface. So you can run it on your tablet, you can run it on your laptop or on your smartphone on the hotspot that is provided by XOMI. Now there are 3 locomotion modes. So the first one is the Ackermann mode. It's kind of driving straight lines and curves, a bit like a car. Then because the 4 outer wheels are steerable, you can also turn on the spot. And what is unique to XOMI is that all 6 wheels are steerable, and thus it can move like a crab sideways without any rotational movement. Now, what we did furthermore in order to actually bring this to the people is...
Miro, just real quick, you've got 4 or 5 minutes left. So we do want to wrap up soon to...
Sorry, I'll just chip in. We are also at the end of the day, so we can overrun it by a little bit, but yeah. Also,
yeah,
that's fair. Yeah.
Okay, sure. I can speed up.
Thank you.
Good. So we have a big wiki. You can basically build this very easily with very extensive instructions. Go have a look at it. We put a lot of effort. Now it approximately takes 2 weeks to print all the parts at home for you, and approximately 2 days to actually assemble it. And it will run you, depending on your parts and what you already own, like 250 to 500 euros. That's similar in dollars. Here's the performance video I mentioned before. So we don't have, I mean, the stone is as big as the wheel, and XOMI just breezes over it. We added a bit more challenge. We added a second stone, and even this is not a problem. I think with a lot of robots, this would be very difficult, especially if they're built for indoor environments. This is not possible, and that's I think the unique selling point also of XOMI is the navigation or the maneuverability in rough environments, and that's where you really see the performance of the triple boogie suspension system shine. This is a setup that is in this lab, the Planetary Robotics Lab, where we have these bedrock slabs, and even on something like this, the grouser and the wheels perform rather well. Then what is actually really nice is a bit of show and giving credit to people. There's actually a lot of people in the world that have already built XOMI. So we have Eric in the US, Peter, I'm not going to say everyone. And this has been just the last half year. I think by now there's approximately 30 people that have built it at least, or that I know of. There's probably more that I don't know of. This is a small collection, because I think without these people, the project also wouldn't be what it is. And this is really what I like a lot to see, when someone randomly posts, hey, I built another one, and then it's in another color combination with other add-ons and stuff like that. Yes, and since there's a lot of interest in the project, and the biggest difficulty for people is to actually find exactly the components, even though we try to make them as easily available. We were thinking of making a kit so people can just buy it. If you're interested, here's the link, the QR code. I will send it afterwards in the chat. You can have a look, fill out the form if you're interested, and then you will get the email if we actually will do a group buy like this. That's it. Thanks a lot for listening. Check out the website, join the Discord, and yeah, follow us on Instagram and Twitter. Cheers.
Wonderful. Thank you so much for that presentation. I love that little robot. It's very adorable.
Yeah, you're welcome.
Yeah, I had a question about the triple boogie system. I've seen like the Mars rover style, but this is new. What are there advantages to this style wheel?
So actually, there has been a study by ESA, and there's a published paper about it, that this system has similar performances compared to the this is the NASA Mars rover style. It's the rocker boogie system, and the big difference compared to it is the simplicity, because with the rocker boogie system, you need a differential. So you need a connection between the left side and the right side of the suspension system. And this is usually either a gearing system or a torsion rod, a complex part, let's say it like this. On the triple boogie system, each boogie is independent, and each boogie is a simple hinge. So it just needs to pivot without any actuation, without any gearing, and that is it. And the performance is similar. So actually you can even have a lower weight with the triple boogie system.
Right, so it's a lot simpler. That makes sense.
Yeah.
So this project is intended for like education. Is this mostly for kids to learn about like assembling and putting together kits, or is this for like new developers to try out software on like a platform? Who's the audience here?
This is a good question, and actually it's something that we didn't know until we built it. We had a guess. We thought, okay, maybe university students could build it and learn to code. As it turns out, the most common people that build it are people from the IT sector, and they want to get some hands-on experience in robotics. And this is a project where they can get very quickly a platform that works with very good building instructions, where they don't have to worry so much if it actually will work. And they can get into 3D printing, they can get into actuation, they can get into sensing. A lot of people, they actually put additional sensors on XOMI. They put a robot arm, so they build and design a little robot arm that they put on XOMI. They add like a battery display showing how much battery is left. They modify it, and the platform is kind of there, and they can use it and build upon it. And it's cool also because it's space and it's approachable, and it has this great maneuverability. And so in that regard, the audience is kind of this builder dude that wants to tinker a bit on the weekend and maybe build something with his son in the free time, you know?
Yeah,
I totally see the appeal to that.
Yeah.
I just want to say, I think that's fantastic, because what you're doing is you're taking the Raspberry Pi, which is a fantastic, a powerhouse tool that we all know and love, and you're, putting that into a robot that then, you're right, with nothing more than a 3D printer and the parts you buy online can be put together quickly. And fantastic that you've put ROS inside of Docker so that you can deploy it easily.
Yeah.
Which means that from there, you're looking at a fully functioning robot with 2 weeks of fun, enjoyable work. And now all you have to do is follow Raspberry Pi tutorials and you can add to it. So it is a fantastic platform in that sense for enabling people to get into it. Obviously, it's got its barriers of cost and time and access to a printer, but provided you meet those requirements, it is a perfect user case.
Yeah, and I totally agree. And I think what is also, in my opinion, what is a bit different to other open source rovers is that we really tried to use only screws, for example. We don't want any metal modification. This was important. And no complicated electronics, so they don't have to make a PCB or even connect jumper cables in a specific way. It's the most complicated is you have to do a bit of soldering, which is like 5 wires. And also the design, because I'm the mechanical designer, so I'm biased, of course, but I think, you can do this with a 7-year-old, build it together, and you can make him draw a hat on an iPad, and then you print it, and then the kid has made the rover his own just by drawing a hat on an iPad, and then the rover has this hat, or changing the mouth.
I've seen 7-year-olds using Tinkercad and 3D printing robots. It's scary how good they're getting at young ages. So they can absolutely start customizing those mouth and head and eyes, and then you'll be scared to leave them alone with it.
Yeah. So I'm just really excited that people are actually building it. This was kind of it. This was really the best thing. Once the first person, Eric from the US, he just sent us a picture with his cat. Hey, I built one. There you go. That was amazing. Yeah.
All right. I think that's all the questions. Anything from the committee?
Yeah, I had a quick question. You mentioned the ROS integration. I was curious if you guys also had gazebo models for them so people could play around in simulation before actually building it.
Thank you for the question. Actually, Calvin, I have good news. This is actually one of the last things I did while working at ESA. I was exporting actually a gazebo model, a URDF model of the whole rover, and it's actually working. I don't know if we ever like announced it or published it like officially, because it was not, we didn't like make the nice tutorial and everything, but it is on the ESA GitHub. It is there, and yeah, people. I think someone even used it. I think someone put it in the nav stack of ROS, which was cool to see. Yeah,
that's fantastic.
Yeah,
nice. We did have one question from YouTube. Have you considered making like some variants that might be like lower cost with fewer motors, or a simpler interface for younger kids or anything?
There are variants possible with lower motor. I mean, with the least you could do with a rover like this is to have 8 motors. If you want to have all the wheels steerable, you just put only 4 wheels. But at the moment, since I'm not working at ESA anymore, I'm not really planning to do anything in this direction. But I think someone could do that for sure. I mean, I built actually a version with 4 motors, but it was not ready to be published. But this was actually a cool internal project at ESA where there was a prototype we wanted to do with 4 wheels, and they wanted to test the locomotion system. And instead of spending, I don't know, 50 grand on building an actual rover, I spent 1 week using the XOMI platform. I modified it to this locomotion specification, and then we had a rover within 2 weeks for 20 euro or 100 euros, you know. And this is possible because it has this, you have the knowledge in this product already, and you can just change the architecture a little bit, and you learn so much by having it in physical. Yeah.
Yeah, that's a great use of it. Okay, I think that's all. Great. So I will pass it on to Oliver to conclude the second session.
Yeah, thank you very much, Chris. Wonderful job hosting. And thank you again to everyone who participated in this second session, as with everyone who's participated in the whole day, whether you're watching from YouTube or you've been involved in the Zoom. It's been great to have you. This has been a wonderful event, and I've really enjoyed seeing the wide variety of different robotics projects that are going on from people who are active within the community. And I'm looking forward to tomorrow because we've got a whole lot more. So it's 10 a.m. EDT, 3 p.m. BST, that correct, Chris? Yeah? Okay, your mic's off.
Sorry, muted. Yes, 10 a.m. EDT. Same time as the last as session 1.
Wonderful. So yeah, we hope to see everyone then tomorrow. Thank you very much.